So my friend's dog, Teddy, likes Sky. Teddy was trying to get a kiss on Sky. Teddy's got a thing for Sky. He's a really funny dog. He's cute. He's younger, maybe 2 years old or so. And today we'll have the introduction, and then we'll finish up chapter 4, cycloalkanes. Pretty sure I'll finish that one. It's called cycloalkanes, but it really could be called cyclohexane, right? Because that's the main one, drawing the chairs and all that. And then we'll start chapter 5, stereochemistry. You can come do lab work during office hours or before my first lab sections, Monday through Thursday. And so yesterday, I think Mary asked, she's in the Tuesday, Thursday lab. Can she come to a Monday, Wednesday before their lab? And I'm like, yep. So anyone can come to these open times. Doesn't matter what lab you're in. And remember to clean off the ATR adapter when you use that on with our IR. Before I left yesterday, whenever I leave lab, I always try to check the IR, and I found that solid on the ATR adapter was forgotten to be cleaned. So I'm pretty sure this solid is benzoic acid, and it's formed from benzaldehyde. And so it happens. It's a teaching moment. I'm not going to point out who did it because I'm not 100% sure, but I'm pretty sure it was someone. I think they know who they are if they remember benzaldehyde, but it's okay. It happens, but we tried not to do that. So benzaldehyde here, it's the cherry smelling liquid. So it's a liquid this is one of the unknowns we've been playing with, and oxygen from the air will oxidize it to benzoic acid, which is the white solid you see here. And it's also used as a preservative. You can add it to soda. These zinc selenide crystal has a zinc selenide crystal. They warned me when I got it. They said don't leave strong acids on it because they can start to eat away at the zinc selenide crystal, and you have to replace it sooner than you want to. So it looks like we have carboxylic acid on here. Is that a strong acid? Does anyone know? The benzoic acid, is that a strong acid? No, it's a weak acid. Its pKa is about 5-ish, yeah. So the pKa of about 5, it's not too strong. So it's not going to damage our zinc selenide crystal too much. So it's not a big deal that it was left there, but it's just a good habit to clean it after you're done. If it were, say, like concentrated sulfuric acid on here, that would be bad. But we don't take IR of concentrated sulfuric acid. Okay, so yeah, that's aldehyde there. Okay, so I gave these study tips last time. I was just saying how if I were you to study for the exam, I would start with the first lecture right after exam 1. I don't know what date that is, but you can figure it out. Right after exam 1, start with that Jamboard and start working through those example problems, and then go to the next lecture. And then after you do that, look at the exit questions, entrance questions, and then do homework, making up your own problems as you go. That'll really prepare you well. Assignment due dates. So the chapter homework C, chapter 3 and 4, you'll want to complete that before our exam that's coming up next week. That due date, I think I'll make it next Monday, Tuesday. I haven't officially made it because I want to make sure I get through chapter 4 today, which I think I will. And then extraction of organic compounds, pre-lab for that. Let's get through, spend an hour and a half at least on it. So when you come to lab today and tomorrow, you're ready to start those. Well, you're probably going to be finishing up extractions, but then after you finish extractions, since you've already pre-lab this one, you can hopefully start working on it right away. And exam 2 next Wednesday, Thursday. I think that's the dates, right? Wednesday, Thursday of next week. Today's the 13th. Yeah, so 7 days. That makes sense. You can see it on the schedule too. Exam 2 details. So all material, all of my exams are cumulative, meaning like all material for the whole year could be on this next exam, but I'll focus on the most recent material. But the most recent material contains most of what was on exam 1. So focus on outcomes 2, chapter 2, 3, and 4, all those outcomes. So if you look at the outcome file, all the outcomes. And then chapter 5, I'll let you know after today's lecture how much of chapter 5 will be on there. I think I want to put a little bit, but we'll see. And then I'll for sure ask you to do radical halogenation of an alkane material, like brominations and chlorinations, fluorinations, something like that. And more specifically, you should know the mechanism, the curved arrow mechanism, the radical mechanism, like in your head. You should be able to see every step of it without even writing it, and then be able to just write it quickly and easily. And predict product ratios as well. So and I'll give you the relative rate data. Like I'll say, oh yeah, the bromine reacts 1,700 times faster at the tertiary than the primary. And then you use that with, oh, there was one tertiary hydrogen 1,700 times faster versus the primary, all that stuff. And then radical reaction coordinate diagrams with Hammond postulates. So we spent a lot of time on that. You will definitely have that, and you'll need to be able to draw them out well and draw the transition states where like, ooh, this bond is just beginning to break, so it's short. This one's almost fully broken, it's longer. And on that Hammond postulate, there's no delta plus or delta minus, no partial charges, right? But I'll also ask you to do a second energy versus reaction coordinate diagram for a polar reaction. So this first one here is a radical mechanism. This will be a polar mechanism. I did one of these, I think, last lecture, start of last lecture. I think I'll do one more quick one just to give you experience with it. And on the polar ones, you will have the partial positive charges. So I want you to say like, ooh, it's started off 0 and it's just beginning to get positive. So it might be like +1/4, or this one was started off negative and it's just beginning to get negative. So it's minus, just beginning to get neutral. It's -3/4, that kind of thing. So practice those. We're going to be reaction coordinate diagram experts at the end of this exam, and we'll use them throughout the semester, throughout the year. Okay. And I'll ask you to predict like 2 acids, which one's stronger, and it won't be 2 acids you memorize the pKa of. You'll have to like draw the conjugate base and say, oh, this conjugate base has a negative charge that stabilized more, making it a weaker base. So the conjugate acid's stronger, that kind of thing. And you'll have to draw out the conjugate base. And some of you were struggling. I haven't graded a lot of the solubility labs. Some of you are struggling with like, if you have an acid and how it would react with water. Or maybe it was on the homework, I saw some struggle. So make sure, don't get confused. Like you should know for sure that an acid, how it reacts with water to make the conjugate base. Sometimes people do it backwards. They make the acid the base. Practice that. And then I may ask an acid-base K equilibrium question. So remember your formula. K equilibrium is 10 to the power of the product side acid minus reactant side acid. That's something we use throughout the whole year too. And then Newman projections. I'm going to ask you to draw some Newman projections and say, like the eclipse are higher in energy, the staggers are lower in energy. And maybe it depends on how long the test is. I might make one of the whole diagram, draw it through 60-degree rotations. And then draw cyclohexane chairs and assess their energies. So I haven't talked about the energies yet, but I will today. So it turns out there's more steric hindrance for the axial positions. So for groups in the axial position, it's more sterically hindered than when it chair flips to become equatorial. And we'll do calculations and stuff with that today. And we're going to draw Newmans of the cyclohexane chairs. They wind up being pretty easy. They're kind of in a way easier than the other Newman projections, than the linear alkanes. And stereochem stuff, more on that. More details later. I'll let you know, see what we get today. More details. Okay, and here we go. We have a new SOTW. I need to get the SOTWs announced on Mondays. I seem to be off lately. I'm always down on Wednesdays, but that's okay. We'll do the SOTW for a while here. A Forest Charter School graduate, homeschool, bio major, will transfer to Sac State, then to Davis. Will be a veterinarian. Competed in 3-day eventing. I didn't know what that was. It's to do with horses, horse jumping and dressage. I think dressage is where the horses go like this. They're all fancy. And horse is named Enzo, named after the Ferrari Enzo. And would like to own a Lamborghini or a Ferrari. Maybe both, I should say. Got married a day before the pandemic shut everything down at Sugar Hill Mill in Sacramento. Got a picture of that. has a dog named Gus and a one-eyed cat named Despero. So here's Despero the cat and Gus. They snuggle up and sleep together all the time. That's something I've always wanted. I totally want to get a kitten for Sky, and I want him to snuggle up and sleep like this. So cute. I love the big long legs all tangled up. Here's a brighter picture of the two of them napping. And Gus is missing one eye, but they did a good job closing it. So when the other eye, the good eye, is closed, you can't even tell. And here she is. That's Enzo. Oh, I don't know if Enzo's male or female, but there's our student of the week, which this is a course near Lake Orville. There's Enzo. Enzo's got sweet mane. Look at how precise that mane is. It's pretty cool. And our student of the week is Annalise Dyer. Let's give a round of applause to Annalise. I love this picture. It looks like she was married on the set of Peaky Blinders or something, huh? All cool 20s look. And so there's her husband, Christian. So they're barely, well, I guess they're a pandemic marriage. They happened during the pandemic, but luckily had a reception and everything before everything was shut down. Okay, and I have something else. Honor student GSAs. Sheet 2 of the Google Sheets animations has honor student GSAs. I finally gotten through the first round of the ones from this semester. So they're Newman projections. And so they're nice to, I would go through and click through them. They're kind of fun and they're not long. And they just help you initially set up the Newmans. They don't rotate, but they're good because that sometimes setting it up initially is the hardest part. And so we've got Aliana, Santos, Ensley, James, Brandon, Raphael. They're all there. Let's look at one more. I think I looked at one before. Let's look at it. I'll show you how you find it. So this is our animations, Google Slide animations, right? And then we got all our like per chapter, but then if you go down here to sheet 2, you'll see the student ones. These are from some from last semester. Actually, you should click on one of these, huh? It'll help you with review the PKA stuff. And I was thinking, I like them all, but I liked, who did, what was it? I'm gonna do Ensley's. I liked her Harry Potter theme. So I honor students, I adjusted your things a litlittle bit. I added some things. Hopefully you're cool with it. So here we are. We've got a molecule here. This is 2,2-dimethyl pentane. We're gonna view from carbon 3 to 4. So now for the Newman projection spell, viewing from 3 to 4. We've added some colorful hydrogens to help us see it well. So Wingordium numinosa. Numinosa. There we go. And we got the carbon 3 in the front there, 4 in the back, and then we got our orange hydrogen on 4 to the left and the blue to the right from Hermione's view. And then we've got the green and the blue. The green would be on the left for Hermione and the blue would be on the right. So there we go. And we got the rest of the carbons up above. Looks good. Ron likes it. Yeah, I know. This is when Hermione was a know-it-all when she was younger. All right, so there we go. And there's more cool ones in there too. We got a lot of check out the other ones too. We have a lot of Marvel themes. I think yeah, we got Tony Stark there. Oh, we got a Hunger Games. I like that one too. Yeah, check them out. Okay, so back to my lecture outline. Any other? Wait, let me keep going. So have you looked over Monday's lecture notes? Have you made up your own problems? I mean, actually, have you worked out last lecture notes? That's what I meant. I can't read. What I mean by worked out last lecture notes, I mean, did you go through the Jamboard, look at the example problems, cover them up, and then do them yourself and check your answers? If you did, you're doing great. If you didn't, you need to do it. And did you make up your own problems afterwards? Like if I gave I don't know, reaction with HBr, you could change it to HI or HCl or something, try something different a little bit and try to make up your own. If you did that and worked out your example problems, then I feel like you're going to be one of the A students on this next exam. If you haven't, get going. And for example, I drew cyclohexane chairs last lecture. And let me make this bigger. That's not full screen. So here is maybe what like an example I did in lecture. I've drawn these two and I'm emphasizing the equatorial, got to point out from the center. And I made everything pointing up red and everything pointing down blue, right? So if I have this example on the Jamboard, quick, cover it up. And now try to recreate it on your own. So I could draw out my chair. Boom, axial up. And I know this is a good axial up here because it makes the letter Y. If I had my axial down, it wouldn't be the letter Y. This is an upside down Y. And then once I have the first one, I can just go and alternate around the ring. So it's axial up, axial down, axial up, axial down, axial up, axial down. Got it. And now I do the equatorials. They have to be pointing out from the center and they point in the opposite direction of their axials. So first one on this carbon, the axial is up, so the equatorial has to be down and out from the center. And the next carbon over, if I go around the ring, it's up and out. A lot of times people make this one to the center, pointing to the center. It's got to be out, down and out, up and out, down and out, up and out. We got it. And I could throw the U's and D's on there, and then number your carbons. And then I like to make sure my carbon number one, if I make this carbon number one the most left, it's still the most left. And it changed from being, foot of a chair to the head of a chair. Carbon 4 was the most right carbon in the head of the chair. Now it's the most right still, but it's the foot of the chair. So you draw them out right. And then all up stayed up and all down stayed down. Oh wait, let me go this. So on carbon 1, you notice how we had an up equatorial. And then now when it flips, the carbon 1 still has up, but it's axial. Okay. And so then after you've done that, you've worked through and checked the answer according to the key, basically the Jamboard, then you make up your own problems. This will make you so much smarter, make studying quicker and easier. You got to initially force yourself to do it. But once you get the hang of this, making up your own stuff, the world opens up. You become a master student. So you might make up an example like this molecule, like, oh, what's that? How do I draw the chair conformations of those? So actually, let's start the lecture with that. And, making up your own problems will make you brilliant. Okay, done with the intro. Any questions? Don't see any questions. Let me get out my iPad. After this chair, remind me to, I was thinking, I said I was going to do another polar mechanism reaction according diagram with Hammond postulates. I think I should give you one more of those. Remind me to do that after this example, please. Okay, first off, I'm going to number this, flat cyclohexane. This is basically, I'm viewing the cyclohexane from the top of the molecule. I'm going to number the carbons, and I like to have carbon 1 on the left here. And in my chairs, I make it on the left. You don't have to do it this way, but if you do it this way, you're doing it the same way as me. So when you're looking at the Jamboard examples, you're doing it the same way. All right, now I'll draw my first chair. That one came out a little thin, but good enough. Here, let me see. Actually, on the iPad, I can maybe circle it. Oh, no, it proportionally changes it. That's okay. That's pretty good. So let me go around and add all my axial and equatorial. So right here, this carbon here, should the axial point up or down? Axial up. So we go axial up and then around the ring. Down, up, down, up, down. There we go. And now equatorial here should point down and out, right? So I'm going to go down and out, up and out, down and out, up and out, down and out, up and out. Got it. They're all pointing out, right? There we go. I got that one. All right, now I'm going to number my chair, and I'm going to number it kind of like I did over here. I'm going to number this one 1. Let me put it inside. 1, 2, 3, 4, 5, 6. So the way I've done this is I've taken this chair and I've lifted it from the alcohol, carbon 6. I lifted that up towards me. See how 6 came towards me? All right, so that means then I can add on all my groups. So what do I have on carbon 1? Do I have like one of the methyl, fluorine, or alcohols, or do I have just hydrogens? What's on carbon 1? Just hydrogens. So I just draw those in. If I'd leave the H, that letter H off, it looks like a methyl. So I don't want to do that. I got to write those hydrogens in. Okay, what's on carbon 2? Just hydrogens again, yep. All right, what about carbon 3? Carbon 3 has a methyl and a hydrogen. So should I draw the methyl equatorial up or axial down? It's got to go up. I'll emphasize it. I'll write a CH3 and then the H axial down like that. I don't have to write that CH3. I could just leave the line there, but I'll write CH3 this time just to make sure you get it. So yeah, that's right. And then carbon 4, what does it have? Just hydrogens. Carbon 5's got a fluorine. So where should that fluorine be? Should the fluorine be equatorial up or axial down? So one way to help you is to know that the methyl is pointing the same direction as the fluorine. So we drew the methyl up. The fluorine also has to be up then. And then the hydrogens below. Does that make sense? How fluorine and methyl are both pointing up in the same direction? And then 6, it's got the alcohol that's dashed back. So is that alcohol going to be up or down? The alcohol is not up. The alcohol is down. Do you see how the methyl and the fluorine have to be facing the same way, and the alcohol has to be pointing the opposite way? So the methyl and the fluorine are up, and the alcohol is down. Okay, so let's draw the other chair. All right, that's a pretty good one. And let's add on the axial, equatorial, all that. So what should the axial be for this one? Should the axial point up or down for that carbon? Down. And then since I have that one right, that's like the letter Y right there, huh? That one's correct. So then the next one's going to be up, down, up, down, up. Okay, and now for the equatorial for this, is it going to point up or down and in or out? Up and out, yep. Up, out, and then around the ring, down, out, up, out, down, out, up, out, down, out. We got it. All right, and now my numbering. I want to number it the same way as I did last time. So in the last one I had carbon was the most left carbon. So carbon 1 was the most left. So should I put carbon 1 over here? No. Here? No. Here? No, here, most left. There it is, right there. Boom, carbon 1. And then the other thing that's tricky is I got to make sure that I pick 2 to be in the right position. So should 2 be up here in the back or should it be out front? Two out in the back or out front? It's going to be in the back. That's got to be 2 right there. And then once I have the 2, everything else just falls in place. 2, 3, 4, 5, 6. Got it. Okay. And I remembered that on carbon 1, I just had hydrogens, so still just hydrogens. Carbon 2 hydrogens, easy. Carbon 3 at a methyl, and the methyl was up. So should the methyl still be up after the chair flip, or should the methyl go down now? The methyl was up, it's going to stay up. Up and down don't change. What changes is the methyl went from being equatorial up to axial up. So up doesn't change, just equatorial axial changes. So always stay up on yourself. Don't get too down. Or if you're down, stay down. Oh, no, that's not good. All right, number 4, 2 hydrogens, easy. Number 5, fluorine is up over here, up equatorial. Or equatorial up. So what should it be over here? Axial up. Got it. 6 has got the alcohol pointing down and equatorial. So equatorial down. So now it should be still equatorial down, huh? Or not equatorial down, I'm sorry. It's got to be axial down. We got it. Done. Okay. So these are in equilibrium. And I want to know, does the equilibrium have an equal amount of both chairs when it's in equilibrium, or do I expect to have more of one and less of the other? Oh, another thing too, I want you to do this. Do-yo on your own. Do on your own. Make a model of this. Do chair flips. With your molecular model kit, make it. Okay, so I'm going to answer your question now, Ryan. So it turns out that the equatorial positions, they're not as crowded. The axials are more crowded. Like when this methyl's here, it's more crowded than when it's equatorial. Type that up. Okay, so the axial positions are more crowded, more steric hindrance for them than the equatorial. So what do you think you want to have axial? Do you want your big groups to be axial or your smaller groups, if there's a, choice you have? Yeah, you want your small groups axial and your big groups equatorial, and that'll make you lower in energy. So what are my largest groups? Let's predict like the size of the groups on this guy. Oh, what did I just do? That's interesting. I did Command A maybe, and I lost my thing. So let's talk about the size of things. So for this example, sizes are, it turns out, what do you think is the largest thing? Hydrogen, fluorine, methyl, or an alcohol? Something about fluorine. Everybody wants fluorine to be the winner of all these rankings because it's so electronegative. But actually, because it's so electronegative, its fluorine is smaller. It pulls its electrons in tight. So the largest group is actually the methyl because it's 4 atoms. So the methyl is larger than the next largest would be the alcohol. And then the next largest would be fluorine. And then the next largest, smallest would be hydrogen. That makes sense, right? It's the smallest atom on the periodic table. I have data about this. Let me show you. Put this, oh, let me take it from here. I'm gonna have to put it on the next slide so it's big enough. So if I look at this guy on my Jamboard, I'm gonna try to do the highlighter. Yeah, there we go. So the hydrogen is the smallest. It's the 0. Oh, that didn't work. I don't like that highlighter. The hydrogen is the smallest, and then the methyl is 1.7. We'll talk about that, and then we're going to compare it to the alcohol is 0.94 and fluorine is 0.25. So what this is saying is that, let's look at the methyl first. So the methyl is 0.25. What's that about? So if I have the methyl in the equatorial position on a cyclohexane, see how it's got a big carbon and 3 hydrogens, pretty big compared to these little hydrogens, right? When it's in this equatorial position, it's got more room, less steric hindrance. It's more stable, lower in energy than when it's axial. When it's axial, these other 2 hydrogens are getting close to it. They're bumping into each other, right? So this is the more stable chair. Lower energy chair. Because there's more room equatorially. Okay. And so what is the difference in energy between having this chair and this chair? The difference in energy is 0.25 kcals per mole. 0.25 kcals per mole lower in energy than when it's axial. That's where that number comes from. What? Why did I say 0.25? It's not 2.5. Does anybody see my error? Sorry, I made the wrong thing. It's this guy. I need to use methyl's number. It's 1.70 times. It's 1.70 kcals per mole lower in energy than when it's axial. That's the one. Yeah. If I though draw the chair, I draw a different chair. Say I draw these both out really quick, and I'll just emphasize the main one. Let's go. If I draw out my 2 chairs here, and instead I say put the fluorine here, and I do my flip, it's here. These are in equilibrium, but it lies more on that side. So this is lower in energy by 0.25 kcals per mole than the when the fluorine's axial. So you can see the fluorine, it doesn't make as big a difference as a methyl because the methyl's a bigger thing. It's got, carbon atom is about the same size as the fluorine, and it's also got 3 hydrogens. And then the OH it's a little higher than the fluorine because an OH has got an oxygen about the same size as the fluorine, plus an extra hydrogen. It's got more atoms, right? It's bigger. Okay, so that's how we use these tables, and just basically it's just size. So a lot of times when I ask people, like on the last question, I said, oh, what's the on the last question I said, what is larger, of the three, fluorine, what's large? Is fluorine the largest? Some people say, oh, fluorine's the biggest because it's the most electronegative, but it's actually it's smaller of the three big guys because, and the energies we see here, they're not based on whether fluorine is electronegative or anything like that. It's just straight size. Steric hindrance is all that's going on here. So fluorine's pretty small, smaller than the chlorine and bromine. Chlorine and bromine about the same. Iodide, I don't know why iodide's bigger, but it has a smaller difference. I don't know what's going on with that one. But you can see the methoxy is bigger. This should be bigger than an alcohol, right? But it's not. Wait. Yeah, that was a weird one too. I'm not sure about that one. Yeah, the general trend though, like methyl gets bigger. Isopropyl, tert-butyl makes a huge difference. And this equation, I'll talk about that more shortly. What it is, it's the Gibbs free energy difference between the two chair conformations. That number is 1.7. That's where I got from here, right? And I can use that to calculate the K equilibrium to see how much of this one I should have at equilibrium, how much of that one. I'm going to do that shortly, but let's go back to this guy here. So for this one, I've got, type it if it looks nicer. I've got my methyl. On this side is axial or equatorial. Equatorial. Oops, I clicked on that. Okay, so the methyl is equatorial on this side, and the fluorine is what? Equatorial as well, and the OH, the alcohol, is also equatorial. So when I compare it to the other side, all those groups now are not equatorial. Now they're all axial, huh? So which one is the lower energy chair? This one. Lower energy chair. That means I'll have more of this chair at equilibrium. And if I want, I can even change the way I draw my equilibrium arrows here. I could say, oh no, they're not, that looks like they're equal. I'm gonna have more of this one and less of that one. That one has the steric hindrance. This methyl is gonna bump into that hydrogen. I know it looks far away, but they're actually pretty close. Okay, and then when you make your model, when you doyo this, you'll see more that the axial positions are more crowded than the equatorials. And then we can calculate proximate energies for these two. So for this side with all the axials, this chair is higher in energy by, for the methyl, it's 1.7 kcals per mole, right? 1.7 plus, for the fluorine, it was 0.25, I think, right? And then for the alcohol, what was the alcohol? 0.94. So let's see how much higher in energy we can. This is an approximate calculation. There's other factors we take into consideration for this, but this is still going to be a good approximation. Okay, 1.7 plus 0.25 plus 0.94 equals 2.89 kcals per mole higher in energy. Okay. So I have another one in my notes here. I'll go over. Oh yeah, I like this one. So This calculation is for this guy here. And I say OChem doesn't have a lot of math, but I think a little math's kind of not too bad. It's kind of fun. So what's going on? We've shown that when the methyl is axial, it's higher in energy. It's more sterically hindered. And then when it's equatorial, it's lower in energy. How much difference in energy? 1.7 kcals per mole. So if we use the formula delta G equals negative RT ln K equilibrium, if you remember that one from back in the day, we can set that equal to 1.74. And then we put in an R value, the gas constant that has the right units. So we can use the 2 times 10 to the negative 3 kcals per Kelvin mole, because it matches up with kcals per mole here. And then the temperature is in Kelvin. So we're going to go room temperature, 298. So at room temperature, if I plug in my numbers and I solve for ln K equilibrium, it would equal to, delta G over negative RT. Put all those numbers in, I get ln K equilibrium is negative 2.85. Then I do the natural log change here. It equals e to the negative 2.5, which is 0.0577. That's the K equilibrium for this. So my methyl is on the axial on the product side, correct? So does this number make sense, this K equilibrium? What it's saying is that the K equilibrium is the concentrations of the products over the concentration of the reactants, right? And so in this case, it's the axial methyl chair. Because that's on the right, the product side, right? Over the concentration of the equatorial methyl. Okay, so this number is less than 1. So it's saying that, oh, we have less of the axial and more of the equatorial. And so you can then work that out. Let's see what percentage of each we have. Oh, no, no. Okay. So K equilibrium, product over reactants. Oh, I already had it written up here. Let's set the amount of axial chairs to 1, and we'll solve for X. So we get 17. There'll be 17 of the equatorials for every one of the axes. So the percentage of equatorial is, there's one of the, what? This is wrong, huh? Equatorial axial. Huh. Totally wrong. Okay, this should be 17.33, correct? Right there. And then that should be 1. Yeah. So 5% axial, 95% equatorial. So this guy's almost always in it. That methyl's almost always equatorial. I'm surprised I had that error in there. It was an error, right? Doesn't this make more sense? Yeah, equatorial. It's weird. Okay. All right. So we got our percentage of each chair. Yeah, and they have it here, 95:5 ratio. This is from a textbook, and then we confirmed it, right? Okay. I want you to be able to do that. I don't know if I'll put it on the exam though, but it's a good thing to do. So why don't we do this? I'll encourage you to do this. Let's say if you figure out the percentage of each of these chairs, I'll give you some extra credit. So I'll say new extra credit. So what do you think? 1, 2 extra credit points? I think it's +1. Just one calculation. Calculate. What happened of each share? Below. So you're doing the exact same calculation I did on the last slide, but instead of using the initial 1.7 kcals per mole, you're going to use the 2.89 kcals per mole. And do the same calculation. Oh, I got it right there. So for you math heads out there, you'll be like, oh yeah, cool, it's easy, no worries. Delta G equals negative RT L natural log of K equilibrium. And it also equals 2.89. But it should be, oh, it's positive 2.89, yeah. Because it's not product favored. Let me see the other one. Positive, yep. Okay, we are good with the sign and everything. Kcals per mole. Okay, some nice little quick extra credit while you're reading over your notes practice. Okay, so now let's do another one. Let's get good at the just drawing them and predicting them. So remember how I said I want you to go through these examples? Yeah, go through these examples. And after you've gone through the examples, writing it out yourself and checking your work, then you're going to make up your own. I'll show you it's easy to make them up, especially these ones. I'll draw out another cyclohexane here. A flat. I'm going to go flat again to chair. That guy was ugly. I have trouble drawing cyclohexanes on the sides, but it's kind of nicer to do it this way. Okay, so now on this one, I'm going to number the way I like to always number. I'm going to go 1 here and then 2 up above. I'm going to do them numbered on the inside. Okay, 1, 2, 3, 4, 5, 6. Okay, so tell me what you're going to help me make this example problem. I want to show you it's easy to make up your own problem. So on carbon 1, what do you want? Do you want 2 hydrogens? Do you want a methyl, ethyl, something else, tert butyl? I see a chlorine. Okay, chlorine. So do you want this chlorine to be, do you want it to be just 1 chlorine or 2 chlorines on carbon 1? 1 chlorine. Do you want it to be wedged or dashed? Wedged it is. Okay, we got a chlorine on carbon 1. Carbon 2, what do we got? 2 hydrogens, something, an ethyl, a methyl, tert butyl, alcohol. 2 hydrogens on carbon 2. Shayla called it. That's what we're going to do. Carbon 3. Terbutyl. Okay. And then the terbutyl on 3, do you want it to be wedged or dashed? A wedged terbutyl. Terbutyl is a tertiary butyl group. It's 4 carbons. So I got 1 there, 2, 3, 4. Kind of looks like a chicken foot or something. Terbutyls are big. They want to be equatorial. Okay, 4. A fluorine on 4. Want it wedged or dashed? Wedged it is. 5. Tell you what, I'm gonna make 5 have something dashed because we have all wedged. We don't have to, but so what do we want to put on the dash position for 5? My phone. Oh, that's. We got these new phones in our office. They have a weird ring. Okay. Want to just keep that a methyl? Oh, Ryan asked for an alcohol. Okay, alcohol it is. All right, so let me draw this. So I'll draw out the first chair. Draw out the second one too, why not? And I'll number it. The same, I'm gonna call my leftmost carbon 1, because that's what I did up above, leftmost. And then carbon 2, I'm gonna put it here. I could put the 2 here, but then, I don't know, it seems a little more confusing to me. 3, 4, 5, 6, okay. Let me add on my axials first. So it's axial up, axial down, axial up, axial down, axial up, axial down. Equatorials, equatorial out, down and out, up and out, down and out, up and out, down and out, up and out. There we go. And now carbon 1 has got a chlorine, and this chlorine is wedged up. So when I take this molecule, I'm going to actually take it and I'm going to grab the alcohol and pull it up towards me. And because I grab it and rotate it that way, the wedge groups will be pointing up. So the chlorine will be up like this. And then H here. Carbon 2, it just has hydrogens. Carbon 3's got a terbutyl up. There we go. And a hydrogen down. Carbon 4, fluorine up. Hydrogen down. 5, hydrogen up, alcohol down. 6 has got hydrogen. There we go. Okay, so let me check this one out real quick. I've got my chlorine is equatorial. Actually, I'll do it on the computer. It looks so much nicer. My chlorine is equatorial, looking good. The tert-butyl is equatorial as well. And the fluorine, though, is axial. And the alcohol, axial. Okay, so that tert-butyl and the chlorine are pretty happy equatorial, but the fluorine and the alcohol aren't so happy. They have to be axial. When they chair flip, I want to still have this be carbon number 1. And then this is still 2. It's got to go around the back like that. 3, 4, 5, 6. Okay. Add on my axial equatorials. Axial, up, down, up, down, up, down, up. Got it. Equatorial, down and out, up and out, down and out, up and out, down and out, up and out. Got it. Carbon 1 has a chlorine. It still should be up. Now it's just axial up. 2, hydrogens. 3, tert-butyl, axial up, hydrogen down. 4, fluorine up, equatorial now. Down. 5, the alcohol still has to point down. 6 is hydrogens, good. So for this one, everybody switch. So the chlorine is axial. The tert-butyl is axial. Wait. I got cap locks on. I like it lowercase with the dot. And then the fluorine now became equatorial. And the alcohol too. Okay, so which one do you think is more stable? That I spelled comparison. I can't spell so bad. Compare, I'll just say size compare. So I've got, for the more stable, the one on the left. Let's check. So the largest group of all is the tert-butyl by far. If you look up its value for differences in energies, it's tert-butyl right here. It's right here. 5 kcals per mole. Big difference. Tert-butyls. 5 kcal. So when it's axial, it raises the energy of the chair 5 kcals per mole. So that's the largest group. The next largest, does anybody have a guess? I'm gonna go alcohol too. Pretty sure it's the alcohol. Let's see. The alcohol 0.94. Yeah, that's the one, 0.94. Kcals per mole. I'll leave the unit off. I hope you'll understand that. Then what's bigger, chlorine or fluorine? Chlorine's bigger. I'm gonna write about both out and then I'll fill it in. And fluorine's the smallest. Let's see what their values are. Chlorine, fluorine. Chlorine is 0.52, 0.25 for fluorine. Yeah, so you can see the tert-butyl overrides all these other dudes. So if the tert-butyl is chemists actually, when they put the tert-butyl on a cyclohexane ring, you think of it as like you're kind of locking it in that chair conformation. So this side's low energy, more stable. And I can write up my equilibrium arrows a little better now, huh? I can say, oh yeah, no, it's more like this. Big time this way, barely any of it goes that way. This is lower in energy by what is it? It's going to be 5 plus, what else is equatorial? Chlorine, 0.25, 0.52, I mean. My goodness, why can't I? Oh, 0.52 minus the 2 axials, 0.94 minus 0.25 equals, let's see, 5.52 minus 0.94 minus 0.25, 4.33 kcals per mole. So that's a lot more stable. So if we compare it to other ones like this one, we got not that one's, this one's not even 3. And the first one, remember when this was only 1.7 kcals per mole difference in energy, and you still made 95% of the lower energy. So when it's 4.3, it's going to be like 99.99% of this chair or something like that. Polar reaction coordinate diagrams. So I got one here. We have tert-butyl iodide. So let's show you this guy right here. This is what kind of iodide is this? Is this a methyl iodide? A primary iodide? A secondary iodide? Tertiary? What do you think? Tertiary iodide, yep. The carbon with the iodide has 1, 2, 3 other carbons. So this guy is a tertiary iodide. All right. So I'm going to start the mechanism. Oh, well, before I do that. So the tertiary iodide is going to become a tertiary alcohol, T-butanol, and you'll make iodide and hydronium. So let's see the mechanism for it. That's the overall reaction. First step of the mechanism is the iodide breaks off. It's a weird one. All by itself, it breaks off like that. And it makes a carbocation. The carbocation has got some things to help it out. It's short electrons, but it has 1, 2, 3 sp3 carbon neighbors next door, and they can donate electron density into it, help stabilize it, like a same situation like with the radical. Okay, and now the next step is a water molecule adds on to this. That carbocation draws the oxygen in because the oxygen's delta minus, right? Carbocation is positive. Opposites attract. Boom. Oh, I didn't draw that right, did I? So red right here. And so that adds, and you can see we're almost to the final product, huh? Almost got my alcohol, it's just protonated. And the last step is another water molecule comes along, deprotonates. That there, and then right here. There we go. That's our full mechanism. But we need, for a reaction coordinate diagram, we need a little more details. This step here, that's the rate determining step, and it's endothermic. This next step is exo. It's not rate determining, it's a fast one. And the last step, it's exo as well. And the overall reaction is exothermic. Okay, so we have our mechanism drawn out. On the exam, I could give you like the mechanism drawn out, but I probably wouldn't. I think I would have like the products and reactants and intermediates, but no curved arrows maybe. Have you drawn the curved arrows? That would be a good question, I think. I'm going to shrink this down for us so I have more room for my reaction coordinate diagram. I'll post it on the next panel. But for people reading over this, go to next. Okay. There we go. Okay, here we go. Got some more room to work with. Energy. Reaction coordinate. First step. Endothermic. So I start off with my iodide by itself. And it does look like a crazy step. We know it's endothermic because we're just breaking a bond. The carbon iodide bond is breaking. So I draw my products for that step. And add in my activation energy. this, like I say, rate determining step, draw in my transition state symbol 1. Okay. And now for the next step, the carbocation needs a water molecule to come along to add to it. So I'll add on a water molecule. This step's exothermic. I can put it, you know, in this area. It could line up perfectly with this or go all the way down. I'm going to put it here, but any of those positions, if you did it differently, are fine. I want to make sure that this next activation energy isn't as long as the first one, because that first one's the rate determining step. And now the next, let me draw my products. I have protonated alcohol right now. And I know from my mechanism, I need to have another water molecule come along and deprotonate it. So I need to draw in that next water molecule. Boom, boom, boom. There we go. And I know that this has to be exothermic overall. If I look here, it's got to be lower in energy than the starting one. My activation energy needs to be less than the first one, but it could be larger than larger or smaller or the same as the second one. We don't really know, have enough information for that. All right, we got 3 transition states and my products now, 2 final products here. The alcohol and hydronium. Okay, and this again is exothermic overall. Okay, now let's draw some transition states with the Hammond postulate. So transition state 1. I'm going to draw this out in a way I hope it will help. Let's do this. We'll do react. I'm going to draw out the mechanistic step to get this there. So we'll go reactants. You know, I'm going to do it on the next panel. So transition state 1. So the reactant is the tertiary iodide. Oh. And then the product is the carbocation, and then the iodide really far away because it's now a separate molecule floated off. It's going on its merry way. The transition state will be between these. So the transition state is here in between reactant and product, right? So does that transition state look more like reactants or products? Let's go back. So it's right here, transition state 1. Is it closer to the products or reactants? Looks more like the products. And the products have the iodide super far from the carbocation. So the transition state, if I want to exaggerate it, should look something like this. The iodide really far away. And dots, dot, 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 all the way across. Okay. And in the product, we have a -1 charge iodide. If this looks more like the products, what should the charge be? Should it be like -1/4 or -3/4? It should be more like -3/4. It should be closer to -1. Good. And then my carbocation, it starts off 0, ends up +1. What should it be now in the transition state? Like a +1/4 or +3/4? 3/4, because it's looking mostly like +1. I think some of you wanted that those two fractions to kind of be like complementary or something. I don't know. Maybe you could think of it as this. Let's see, we got 0, -1, +1. We started off with the carbon at 0. It's going to +1. The transition state's closer to +1, right? A late transition state. Okay, so let me draw it out again over here real quick. And +3/4 by that carbon, -3/4 by the iodine. Got it. Transition state 2. Let's do it. I saw a lot of you had +1/4. Is it making sense again? On the chat, you made a little error there. Transition state 2. So here we go. On this one, we have for our reactants, a carbocation and a water molecule. And initially, they're different molecules. They're far apart. They aren't reacting yet. But in the transition state, what are they going to look like? Because at the product side, they are connected. Oh, I went red with this, didn't I? I forgot. So this has got to reach over and add into this, right? So what does our transition state look more like? Does it look more like reactants or more like products? Yep. I think I should make a statement here too. Normal, blue. And that was transition state 1. Transition state 2 here, this one's a little different. It looks more like reactants because it's exothermic. Okay, so it's going to look more like reactants. So this new bond that's forming, it's going to be long. Super long, right? What about the charges here? This carbon starts off at +1, but ends up, I'm sorry, carbon starts off at +1, yep, ends up at 0. Is it going to be closer to +1 now or closer to 0? Closer to +1, plus like 3/4. And then the oxygen starts off 0, ends up +1. So in the transition state, if it looks more like reactants, it's going to be like plus only 1/4. It's going to be less positive. Make that more clear. Hold on. +1/4. Yep, there we go. You got it. And then go back to here and say, yeah, I'll draw that up one more time. Let's go. Water's far away. +1/4 plus 3/4. Got it. Transition state 3. Let's go to another panel. Let's draw it out nice and big. I'm hoping this new way I'm drawing these out is helping. Something I thought of this year. I've never done it this way before. So in transition state 3, our reactants. Did I write reactants, products? I didn't write products over here. Our reactants look like protonated alcohol. And really far away, another water molecule. And that water molecule is going to reach out its lone pair to break that guy. So the transition state what will it look like? More like reactants or more like products? Transition state 3, reactants or products? Reactants. Yep, reactants it is. I could take this I got the same thing here. Oh wait, this is supposed to be transition state 2, huh? Let's draw it. Transition state 3. This bond is just starting to break because it looks more like reactants. And then the other bond to the water is really long because it's only beginning to form. Okay, what about the charges? We're looking more like reactants. So the carbon, oh no, this oxygen starts out positive. So this should be plus what, this oxygen? 3/4 or 1/4? 3/4. And this oxygen starts off 0. So it's going to become positive, but right now in the beginning, it's only like a little positive, like plus 1/4, huh? Got it. So that's panel 7. So hopefully it's all going good now. Might help to do sound effects as you draw the transition states. There we go. Did it. Done. Okay, so let's shift gears back again. Now we're going to do Newmans. I'm going to take this guy. Oh, I didn't do it right. You're welcome. You know what? Put this right next to there. I think it's better. No, I'll do it in order. So Newman projections of cyclohexanes are actually surprisingly not that hard. I'll show you what we do. Filling up the Jamboard today. We're on panel 11. We're going to start using more and more Jamboards, more me drawing stuff out than in the beginning. It's a lot of like nomenclature. It's not nomenclature, but just explaining things. Let me show you what's going on here. We're going to look at a Newman projection where we take and we look down 2 bonds so we can see We're going to look down this bond, say, and this one. So this Newman we're checking out, it's looking from carbon 1 to carbon 2, and also at the same time looking carbon 5 to carbon 6. Do you see how that, this is 5 to 6 here, 1 to 2. Oh, wait, no, that's not 6, that's 4, huh? I can't read my own number. 5 to 4, huh? Yep, 6 in the middle. All right, so this is how we draw these. We start off by drawing them 2 circles. The big, I like to draw the big back carbons first, and then the dots. So it looks like owl eyes. And then I'll number some carbons that I already know. This will help me keep track of things. This first dot here, the pupil of that eye is 1. And then the other one is 2, the circle. That's 2. And what's the pupil on this side? What is that? Carbon. Carbon 5. And then this one in the circle is 4. Okay. And now to get started on this, I like to connect 1 to 5, this front to the front. I like to connect them, and I have to figure out for the chair conformation I started with here, do 1 and 5 connect to 6 going up, or do they connect going down? Which way are they going? If you look at your chair, doesn't 6 look up? It's up compared to 1 and 5. So then, okay, 6 is up. I can do this. I just go up like this. There we go. I got my 6. Once I have that, I think the rest of it just kind of falls into place, because I know I need to have like a Y shape on 1 and 5, right? So since it has to be a Y shape, I just go, oh yeah, I just go whoop, boom, boom. There's my Y, boom, boom. And these are going to be, for each chair, it's either going to be a right side up Y like this or an upside down Y. Okay. And then after I do that, I can remember from the beginning of this chapter, I said cyclohexane chairs are important because they allow all the bonds to be staggered, right? No eclipsing. So if I know they're all staggered, then I can be like, oh yeah, staggered. I know where that is. That's like, you know, right in the middle. Staggered, staggered, boom, boom. And then this back one is going to be where they connect like that, boom, like that. Yeah. So let me number my carbons. Number 1 is there. I'm looking at 2 in the back. I already actually labeled that 2, didn't I? And then that number 2 attaches to 3 right here. Do you see how 3 went down from 2? And when you look at the chair up above, 2 down to 3, right? Back up to 4, 5, 6. We got this all numbered, huh? 1, 2, 3, 4, 5, 6. Yeah, we're all numbered. Looks good. So now we'll just start adding on our groups. Carbon 1 has a chlorine up equatorial. So you can hopefully see that that's where it's got to go, up equatorial. And it has a hydrogen. Carbon 2, just 2 hydrogens. Carbon 3. Now the carbon 3 is a little tricky. It has a hydrogen straight down. Do you see that guy right there, the axial? And then it's got a tert butyl pointing away. I'll show you a couple ways we can represent this. One way is to draw a circle, because that's what's behind us, right? And then just label this as tert butyl, T-butyl, saying it's pointing back away from us. Or another way to do that is you can do a Newman and a Newman. So, or a Newman in a Newman. So I'll draw this partially here for you. So it'll be like this. I got that part going, right? I'll just, and then there's a carbon back there. And then that carbon has 3 methyls off of it. See what I did there? This here is my Newman in my Newman. It's got 1, 2, 3 methyls, the 1, 2, 3 methyls of the Newman. If you're not comfortable with that, you can just write T-butyl. It's okay. I know it's kind of tricky. Okay, number 4, I've got the fluorine up, hydrogen down. 5 has got the alcohol down, hydrogen up. I don't know what's going on here. There it is. Hydrogen up. 6 has got a hydrogen going up, right? The axial. And then the 1 hydrogen coming at you, we draw this as a dot. Hydrogen coming at you. And here, I don't have this exact model made up, but let me show you what I mean by this. So can you see me on my little screen? I'm holding up a cyclohexane chair, and I'm holding it up in a way where I'm looking down those 2 bonds, the Newman projecting bonds. This white one coming right at you, I drew as a dot. That one I drew up. That's carbon 6 right here. And then the rest of them, you know, we're looking right down those bonds. And then this is the hydrogen going down, and this is a tert-butyl, this back one here. Okay, so definitely doyo this one. Make the model. Doyo. Do on your own. Make this model. All right, so now there's a chair flip for this as well. Just like before, this is the lower energy chair. If you remember, we calculated before. Now let's do the higher energy. So I start off my 2 allyls. All right, and then I'll number some carbons. Oh, and also let me show you what we're doing here. We're still looking down carbons 1 to 2. Carbons 1 to 2. And we're still looking down carbons 5 to 4. It seems a little strange, huh? How you're looking at it kind of from a different angle now after the chair flip. But we still have carbon 1 right here, still have carbon 2 right there. This is still 5, and this is still 4. And the key thing to do with these is to make sure you connect 5 and 1 correctly again. So before 5 and 1 were connected going up, right? Because the 6 is definitely higher than 5 and 1. What about now? If I've got number 1 and 5 are my focus, is 6 down or up?
Mark, you have a little window in front of the drawing you have, like a little font window.
Is everything okay now?
Oh, sorry, I did. Geez, I'm sorry.
No worries.
I couldn't tell whose screen was whose. Sorry.
It's okay. Definitely speak up if something seems wrong. It's fine. Okay, so should I go to 6? Should 6 be up still, or should it be down now? So I got 1 here, 5 here, 6 is down, huh? See how 1 goes down to 6, 5 goes down to 6? Yeah. And so I draw that. I go 6 is right there. It's connected like that. This 2 is looking a little strange. 6 is right there. And it also makes sense that 6 goes down because you can think like, well, 6 was, say, the head of the chair on this cyclohexane chair, and now it's the foot. It just did a chair flip, you know? All right, so now I can add on the rest of my groups to carbon 1 and 5. Hopefully it's obvious. This is an upside down Y this time. Before it was a right side up Y, now it's an upside down Y. And they're still all staggered, so I'll draw Staggered, meets in the middle. Oh, that one wasn't so good. Staggered meets in the middle. Staggered. Trying to make this look prettier. There we go. Now let me put all my numbers on there. 1, 2. This is 3 now. Still in the back. 4, 5, 6. Okay, we're good. Yeah, just add on my groups. Carbon 1. Got a chlorine up. It was, and the other Newman up equatorial. Now it's up axial. Carbon 2 has hydrogens. Carbon 3 has a terbutyl pointing up axial. There it is. That's easier to draw. And then a carbon, the other hydrogen is actually pointing away. This is the hydrogen away from you. We just draw that as a circle. Carbon 4, got the fluorine up. And hydrogen out. Carbon 6, 2 hydrogens. One's pointing down axial and one's pointing right at us. That's the dot. So when you have a black dot like that, and nothing's attached to that dot, that's a hydrogen. When you have a circle with nothing attached to it, and no one telling you otherwise, it's a hydrogen. This time, over here on the left, it looks like it could be a hydrogen, but I say no, it's a terbutyl. Or I do I like it, inception of Newton, whatever Brian was saying. I do a Newman in a Newman. Okay, so those are Newmans. We can do Newmans. We'll practice some in lab. I'll get you good at it because I know it's been a long lecture and I did it at the end of the lecture. So we are basically about done with chapter 4, but I didn't get to chapter 5. I think I might just put something really basic from chapter 5 on exam 1 because chapter 5, I would have to present that on Monday for the Wednesday lecture, but I think it'll be good just to give you something super simple.
Mark.
Yes.
We forgot the alcohol.
I did?
And the carbon 4 is
Carbon.
attached. The hydrogen is attached to the 5.
Yes, it's right here, huh? It's down, huh? Thank you. I rushed it. Oh, I didn't even do carbon 5 at all. And it's hydrogen, huh? Yeah, thanks for that. Yeah, I forgot that. Okay, so we're almost done with chapter 4. Monday, I'll just do the last little bits of chapter 4. It's kind of just like fun facts type of stuff. Trans-cis-decalin, these guys. I'll let you know Monday whether I'm going to have any of top 5 on the exam 1, and maybe I won't have any. We'll see. But you have plenty to keep you busy with your other studies for this exam 1, exam 2.